So now we'll discuss what is most economical channel section. A channel section is considered to be most economical or most efficient when it can pass maximum discharge for a given cross-sectional area, resistance coefficient and bottom slope. So that means for a constant cross-sectional area or a constant resistance coefficient and a constant bottom slope, if the channel is carrying maximum discharge, then it is known as most economical. So you know that for from continuity equation, discharge is area into velocity. So we said that for most economic channel section, the when area is a constant, so velocity or discharge has to be maximum. So if discharge has to be maximum, then velocity should be maximum. Okay, so now the condition is that for maximum discharge, velocity has to be maximum. So therefore, when you come to Chassis equation or Manning's formula, when we V is equal to C root RS. So if V has to be maximum, then because C is constant, S is constant, so R has to be maximum. Similarly, if you take Manning's equation, if V has to be maximum, then R has to be maximum if N and S are constant. So now if R has to be maximum from hydraulic mean radius A by P for a given area, that is area as a constant, if R has to be maximum, then wetted perimeter has to be minimum. So therefore, if the channel section has to be most economical, it has to carry maximum discharge. For maximum discharge, wetted perimeter has to be minimum. So this criteria is utilized in determining the dimensions of the most economical channel sections of different forms like rectangular, trapezoidal, like this, circular channels or triangular channel sections. So coming to most economical rectangular channel sections, you can consider a channel of width B and depth of flow Y. So what are the conditions or what are the relations between B and Y is to be determined. So now water area is it is the cross-sectional area of flow which is taken normal to the direction of the flow. So therefore it is B into Y. So A is B into Y. So therefore B is A by Y. So you know that the wetted perimeter is length of channel boundary in contact with the flowing water. So it is B plus 2Y. Substitute the value of A by Y here. So it will be P equals A by Y plus 2Y. So now P is a function of Y only. So if we know that the wetted perimeter for most economic channel sections, wetted perimeter should be minimum. So if you differentiate wetted perimeter with respect to depth of flow, so then and put it equal to 0. So you know that P is equal to A by Y plus 2Y. So differentiating, so since A is a constant, so it is minus A by Y square plus differentiation of 2Y is 2, so it will be equal to 0. So therefore, the first condition is that the water area has to be 2 times Y square, 2 times Y square. But you know that A is B into Y. So should be equal to 2y square. So y cancels. So therefore B is 2 times the depth of flow, or the depth of the flow should be half the bottom width. Half the bottom width. So this is the condition. Also hydraulic mean radius R is A by P. So since A is 2y square and P is B plus 2y, from condition 2 we found that B is equal to 2y. So therefore 2y square divided by 4y. So therefore hydraulic mean radius is y by 2. So what are the conditions for the rectangular sections? The conditions for rectangular section is A is equal to 2y square. So B is equal to 2y and R is y by 2. So therefore, it can be seen that for most economical sections, the depth of the flow is equal to half the bottom width, or hydraulic mean radius is half the depth of the flow. So now consider the most economical trapezoidal sections. So if B is the bottom width, Y is the depth of the flow, and the side slopes are 1 in Z. So we know that the water area is A equals Y into B plus ZY. Okay, now taking out B from here, so A by Y, okay, is equal to B plus ZY. So therefore B is A by Y minus ZY. Now you write an equation for P, which is B plus 2 sloping sides, that is B plus 2y root of 1 plus z square. Substitute the value of B from equation 1. So it will be A by Y minus ZY plus 2y root of 1 plus z square. Now we know that for most economical channel section, the wetted perimeter should be minimum. So therefore differentiating this with respect to Y, keeping A and Z constant. So then it is minus A by Y square, here minus Z. So differentiation of Y is 1, and again differentiation of Y is 1. So plus 2 into root of 1 plus Z square should be equal to 0. So there is the same thing is written again. So therefore now we have this differentiation of dou p by dou y. Again we have written here. So dou p by dou y is minus a by y square. So minus z plus 2 into root of 1 plus z square. So rearranging the term, putting on the other side, a by y square plus z should be equal to 2 times root of 1 plus z square. But you know that a is nothing but y into b plus zy. So y and y gets cancelled out. So then taking LCM, so it will be b plus zy into zy by y should be equal to 2 times root of 1 plus z square. Rearranging the term, so we get b plus 2zy by 2 should be equal to y into root of 1 plus z. You can see that b plus 2zy is the top width. So it is the half the top width should be equal to length of one of the sloping side for most economical channel sections. Also, hydraulic mean radius r can be expressed as r is equal to a by p. But what is a? It is y into b plus zy. So what is p? It is b plus 2y into root of 1 plus z square. So now you know that, so from this equation you know that 2 times y root of 1 plus z square is b plus 2zy. So substituting 2y root of 1 plus z square as b plus 2zy. So b plus b is 2b. So therefore plus 2zy. So 2 comes out. So therefore it is b plus zy. So b plus zy, b plus zy cancels out, and we know that hydraulic mean radius will be equal to y by 2. So therefore for most economical channel sections, hydraulic mean radius must be equal to half the depth of the flow. So these two conditions are utilized in solving the problems. So now take a trapezoidal section again. So now this is the top width. So take the center of the top width, which is O. Then from the center drop a perpendicular to one of the sloping side. So let it be OA. If this angle is theta, so this angle is also theta. Okay, so now let theta be the angle separated by the sloping side with respect to horizontal. Now taking the triangle OAC, so we have sine theta as OA by OC. Okay, so therefore OA should be equal to OC sine theta. So which is equation 1. But OC is known because the total top width is b plus 2zy. So therefore OC is b plus 2zy by 2. So that is one thing. And also sine theta. What is sine theta from this equation? Sine theta is, so this is perpendicular by this length, sloping length. So it is y divided by y into root of 1 plus z square. So y cancels. So sine theta is 1 by root of 1 plus z square. So now you can take this OA, and now instead of OC you can substitute as b plus 2zy by 2, and instead of sine theta you can substitute as 1 by root of 1 plus z square. So using the relation that we derived from most economical sections, b plus 2zy by 2 is y into root of 1 plus z square. So therefore now wherever there is okay, so b plus 2zy by 2 you can substitute as y into root of 1 plus z square. So this gets cancelled out and you are left with OA is equal to y. So that means we have the perpendicular distance OA is equal to y. So now if you take O as the center and radius equal to the depth of the flow, so the three sides of the most economical channel sections will be tangential to the semicircle. So this is how you can prove. So sometimes in the data that the theta value will not be given or side slope will not be given. So then what side slope to be taken in the derivation? So what or in the problem? So water area is A is equal to y into b plus zy. So b you can express in terms of a by y minus zy. So substitute the value of b here in the perimeter. So that gives p equal a by y minus zy plus 2y root of 1 plus z square. Now keeping a and y as constant, and you can differentiate with respect, make the slope variable, so you can differentiate with respect to z and put it equal to z. So therefore differentiating this with respect to z, we have okay, a by y this will be 0. So differentiation of z is 1, so it is minus y. So 2y, differentiation of root of 1 plus z square, it is 1. Okay, so that is half into 1 plus z square into half minus half into 2z. So that is how it is written. So therefore we have, so y and y cancels out. So you are left with, okay, so 2 and 2 cancels out. So you're left with 1 by root of 1 plus z square, 2z is equal to 1. So now taking to this side and squaring both sides. So 4z square is 1 plus z square. Therefore 3z square is 1. So z is 1 by root 3. Sorry, this is okay. So this angle is theta. Okay, this is z. This is 1. This is theta. So what is tan theta? It is 1 by z. So what is z? It is 1 by root 3. So therefore tan theta is root 3. So therefore the theta should be 60 degrees. That means if the slope is not given, you can take theta as 60 degree for the calculations. So that is z should be equal to 1 by root 3. So 0.577. Now coming to the most economical triangular channel sections. So we have, so let the let this be the triangular sections of depth y and slope is 1 in z. So here let 2 theta be the apex angle. Let 2 theta be the apex angle. So that means this will be theta and this will be theta. Okay. So now we have tan theta is nothing but c. Okay. What is tan theta? It is CB by OC. CB by OC. So what is CB now? It is y tan theta. So therefore this also should be y tan theta. So now you can take cos theta. So cos theta is okay. So that is base. So here okay. So OC by OB. So therefore what is OB? It is nothing but OB is what? OC is y by cos theta. So that is 1 by cos theta secant theta. So therefore OB will be now y secant theta. So what is the area? Area is half 2y tan theta into y. So that means you get a equals y square tan theta, or y is root of a by tan theta. What is perimeter? It is the this sloping side plus sloping side. It will be 2y secant theta. 2y secant theta. Now you can substitute this y here. So substituting, you get 2 into root of a by tan theta secant theta. So 2 root a here written as 1 by root tan theta into secant theta. Now the variable a is a constant, so theta is only the variable. So you can differentiate, okay, differentiate p with respect to theta. So this has to be differentiated with respect to theta and put it equal to 0. So when you differentiate with respect to so you get this equation. So now you have so you differentiate, okay, and then finally, so when you solve this, so when since secant theta is not equal to 0, so you get 2 tan square theta is equal to secant square theta. So secant square theta is 1 plus tan square theta. So therefore tan square theta is 1. So therefore theta should be equal to 45 degree. That means 2 theta is 90 degree. So the right angle triangle is nothing but the most economical triangular section. Okay, now what is hydraulic mean radius? It is a by p. So a is nothing but y square tan theta, where p is 2y secant theta. So if you substitute the value of theta as 45 degrees, so you get y by 2 root 2. So therefore, hydraulic mean radius is nothing but y by 2 root 2. Now coming to the most economical circular channel sections, we know that for a most economical circular section of any radius r, depth of flow, if it varies, the shape of the flow area changes. As such, water area cannot be made constant, as well as the wetted perimeters varies with the depth of the flow. Hence, in case of a circular channels, there are two conditions. That means area of flow cannot be constant, and that cannot be applied here. Therefore, in circular channels, two separate conditions can be derived, for one for maximum velocity, another for maximum discharge. Now, when you derive the conditions for maximum velocity, so you know that you take any Chezy's or Manning's formula. So V is equal to C root RS. But what is R? It is A by P. So therefore, if V has to be maximum, then only A by P, because C and S are constant, so A by P can be constant. So you can differentiate A by P because it is function of theta. So you can differentiate with respect to theta. So that is denominator P, differentiation of numerator, that is d dou A by dou theta minus A into dou P by dou theta by P square should be equal to 0. So since P square is into 0 is 0, so therefore P dou A dou theta minus A into dou P dou theta should be equal to 0. So now the values. We know that A is equal to half r square theta minus sin theta and P is equal to r theta. So dou A by dou theta is nothing but r square by 2. Differentiation of theta is 1. Differentiation of sin theta is cos theta. So 1 minus cos theta. Dou P by dou r. Okay, dou P by dou theta, sorry. Dou P by dou theta is nothing but r. So now you substitute these values A, P, dou A by dou theta and dou P dou theta in the equation 1. So we get finally this term. So that means you substitute P is equal to r theta. You substitute dou A by dou theta here. Then you substitute A and then dou P by dou theta. So after solving, so now cancelling the common term, r square half half. So finally you will get r and r gets cancelled. So r and r gets cancelled. So you will get theta minus theta cos theta like this. Then minus theta here. So minus of minus is plus sin theta. So therefore theta and theta cancels out. So you are left with tan theta should be equal to theta. So now if by solving by 10 error we'll get theta is equal to 257.5. So now you should understand that for maximum velocity condition theta should be equal to 257.5 degrees. So what is the depth of flow for maximum velocity? Then y is equal to r into 1 minus cos theta. But to substitute the value of 257.5, so you will get y is equal to 0.81 times d. So where in terms of r, so r is d by 2, so we will get 0.81 times d. Hydraulic mean radius can also be calculated by substituting in A by P. A is half r square theta minus sin theta, P is r theta. Substitute the value of theta as 257.5, here also 257.5. So finally you will get 0.6086 r, so that way r will be equal to 0.3 times d. So this is how you solve for maximum velocity conditions. Similarly, we'll solve for maximum discharge condition. So now using the same formula, Chassis formula, V is equal to C root RS. So V is equal to C root of A by PS. But we want condition for discharge. So Q is equal to A into V. So A into, so you substitute V here. So now you can bring this A inside. So A cube by P. So for discharge to be maximum, so what should be maximum? It is not A by P. It is A cube by P should be maximum. So if you differentiate A cube by P with respect to theta, put it equal to 0, we'll get the maximum discharge condition. So now differentiate. So okay, denominator differentiation of numerator, okay, minus numerator differentiation of denominator denominator square. So this will be 0. So therefore 3p is that is a square, and this will gets cancelled out. So you are left with 3p dou a by dou theta minus a into dou p by dou theta. Now you can substitute a here, you can substitute p here, dou a by dou theta here, and dou p by dou theta here should be equal to 0. So after simplifying, so we get, so now, so okay, r and r is a const is can be eliminated, half is eliminated, so therefore one more r is eliminated, is all common terms. So you are left with 3 theta, that is 3 theta minus 3 theta cos theta minus theta plus sin theta. So that gives 2 theta minus 3 theta cos theta plus sin theta should be equal to 0. If you solve this equation, then you will get theta is equal to 308 degrees. So that is what you have to remember for maximum discharge condition. If you are using Chassis equation, it is 308 degrees. So put the value of 308 in the depth equation, so that you will get y is equal to 0.95 times d. Similarly, you put in hydraulic mean radius. So here A is half r square theta minus sin theta, P is r theta. So if you substitute theta 308 into pi by, because theta should be in radians, so sin 308, here again theta 308 into pi by 180, you will get r is equal to 0.29 times d. So this is how you solve. So now only difference is that in maximum velocity conditions, whether you use Chassis formula or Manning's formula, but theta will be 257.5. But for the condition for maximum discharge, theta is 308 degrees only when you use Chassis equation. But when you use Manning's equation, it will be slightly different, which I will be showing in the next slide. So what happens when we are using Manning's equation? So here A is equal to, okay, Q is equal to A into V. So V is 1 by n r to the power of 2 by 3 s to the power of half. So in this case, what is R? It is A by P. Okay, so A by P. So substituting here A by P. Okay, so here this is actually A by P means this should be 2 by 3. Sorry, this is 2 by 3. Okay, substitute. Now 1 plus 2 by 3 is 5 by 3. This is p 2 by 3, so make some correction here, so it is 2 by 3. So now you can raise it to the power of 1 by 3 common, so it will be a to the power of 5 by p square. So that's the reason the change in the angle theta takes place as compared to the previous case. Last time it was a cube by p, now it is a to the power of 5 by p square. So if you differentiate this term with respect to theta, okay, then you will put it equal. So if you differentiate, so you will get is equal denominator differentiation of numerator minus numerator differentiation of denominator by denominator. So this will become 0. So now this will get cancelled out with this. So p will go off, 1p will go off, 1p will remain. So therefore what else goes? Yes. So 5p dou a by dou theta minus 2a dou p by dou theta should be equal to 0. So substitute the value of a, substitute the value of p, substitute the value of dou a by dou theta here, substitute the value of dou p by dou theta here, and solve it. Solving, so you get, after substituting, you get here, okay. So now it is r square cancels out, half and half gets cancels out, so then that's all, r and r just cancels out. So therefore you are left with 5 theta, that is 5 theta minus 5 theta cos theta minus 2 theta, then plus 2 sin theta. So you finally will get 3 theta minus 5 theta cos theta plus 2 sin theta. Now if you put by trial and error various values of theta, we'll find that left hand when you put this value 302 degrees, okay, so you get equal to 0, right hand side will be 0. So that's so 302 degrees 20 minutes is your answer for theta when you are using Manning's equation. So similarly, depth of flow has to be, when you put theta value here in y, so you will get y as 0.938 times d. Similarly, maximum discharge for again hydraulic mean rate is for maximum discharge will be r is equal to a by p. Substitute the value of 302 degrees 20 minutes again here, so you will get r as 0.29 times d. So these are the various derivations that were done for the most economical channel sections. So now using the basics of whatever we derived in the most economical rectangular sections, so I'll take up a problem. So rectangular channel is 5.4 meters wide, depth of flow is 1.2 meters, and slope is 1 is to 1000, so which comes to 1 divided by 1000 as 0.001. So Manning's n is given as 0.017. So we have to increase the discharge to a maximum by keeping cross-sectional area of flow, slope, and roughness coefficient same. So now first set of problem is that this is not in most economic channel section because the channel dimensions are already given. So that's why we calculate water area, which is 5.4 into 1.2, which comes to 6.48 meters square. Similarly, perimeter should be calculated as b plus 2y, which comes as 5.4 plus 2 times y, so which is 7.8 meters. So now you can calculate hydraulic mean radius as area divided by perimeter, which is 0.831 meters. Hence calculate velocity by Manning's equation because Manning's constant is given. So 1 by n r to the power of 2 by 3 s to the power of half. So in this case, here it is velocity comes to about 1.644 meter per second. Hence discharge is calculated, which is 10.652 meter cube per second. So nowhere we have used the conditions for most economical channel sections because given the width and then y, so we are finding out various parameters like water area, perimeter, hydraulic mean radius, and then calculating velocity and discharge. Now I want to change this dimension, make it most economical for a given cross-sectional area. So here in this case 6.48 meter square remains constant, whereas slope remains constant, which is 0.001, and roughness coefficient remains the constant. So using this condition, I should find a new value, that is b and y, such that it will be such that the discharge will be maximum. So in the discharge just 10.652 will has to increase in the second set of calculations. So therefore in the second set of calculations I have used here 6.48 meter square, slope as 0.001, and Manning's n as 0.0 17. So I know that a condition for area is 2y square for most economical rectangles. Now I am using the conditions for most economical rectangle section. Since area is told to be made constant, so therefore 6.48 is used, so that gives y. So y is 1.8 meters, but b is another condition for most economical rectangular section, which is 2y. So therefore I get 1.8 and 3.6 meters. So also I use hydraulic mean radius need not be calculated from a by p. So I can use the condition y by 2 for most economical sections, which is 0.9 meters. So hence velocity now can be calculated 1 by n r to the power of 2 by 3 s to the power of half. So which gives 1.734. So now you can see that discharge has increased to 11.236, which was earlier case which was 10.652. So therefore the percentage increase in the discharge is 11.236 minus 10.652, which is 0.584, divided by the original discharge, which is 10.652 into 100, which comes to 5.48 percentage. We have a rectangular section of 5.5 meters wide, and depth of flow is given as 1.25, and the slope is 1 is to 900. So slope is 1 is to 900. So 1 divided by 900 is 0.0011. So Manning's n is given. So here I have taken 0.017. So therefore this is 0.017. So now here we have to find the dimensions such that the discharge is maximum. So that means it will be most economical channel sections. So first set of problem, that is first set of data, is to calculate what is the discharge for a given width and the depth of flow. It is not most economical channel section. So as usual, you find out the area, that is 5.5 into 1.25, which comes to 6.875 meters square. Then the perimeter is calculated by b plus 2y. So therefore we are using b as 5.5 and y as 1.25, which gives 8 meters. So similarly, hydraulic mean radius is a by p, which comes to 0.8594, and then velocity is calculated by Manning's equation, 1 by n r to the power of 2 by 3 s to the power of half. So that comes to 1.7635, and hence discharge is calculated. So now the discharge is 12.124. So what is given is that you have to increase the discharge by keeping the same quantity of lining. So lining is always given on the perimeters. So therefore it is not, in the first problem the area was constant. In this case the perimeter is the constant. So therefore when you take the second set of data, so for most economical, the perimeter you should keep constant, with slope constant and Manning's n constant. Or in the second set when it has to be made most economical, we have to find the value of b and y, for which perimeter is 8 meters, s is 0.0011, and n is 0.017. So for most economical rectangles, we are using a relation b is equal to 2y. So what is perimeter? B plus 2y, but b is 2y. So therefore this p is nothing but 4y now. So since p is given, which is 8 meters calculated from the previous calculations, so we can make use of this and then calculate y. So we get, then b is 2y, so therefore the dimensions are b is equal to 4 meters and y is equal to 2 meters. So now the area which you had calculated the previous, it doesn't hold good. So new calculations, that is b into y, that is 4 into 2, it comes as 8 meters square. So R is also using the most economical condition, which is y by 2, which comes to 1 meter. So you can calculate V is 1 by n r to the power of 2 by 3 s to the power of half, which is 1.951, and hence discharge is increasing. So discharge increased to 15.608 from 12.124. So therefore the percentage increase in discharge will be 15.608 minus 12.124, which is 3.484, divided by the original discharge is 12.12 into 100, comes to 28.74 percentage. So these two problems were taken for the most economical rectangular section. In the first case, it was given that the area of section or area of flow section, then the slope and the coefficient is a constant for most economical channel section. Whereas the second problem, it was said that it is the same quantity of lining. That means the area is not a constant, the perimeter is a constant, and the slope and as well as the Manning's constant or rugosity coefficient is constant. So that's the problems on rectangular channels. So now we'll take problems on trapezoidal channel sections, which are very important. So we know that trapezoidal channel will carry 132 meter cube per minute as a discharge. So divide by 60. So you will get, to convert into meter cube per second, so we'll get 2.2 meter cube per second. It is designed to have a minimum cross section, in the sense that it is the most economical channel sections. We have to find the bottom width b and also depth. If the bed slope is given as 1 is to 1200, Okay, so that is given, and chassis constant is given. So what is the first condition to be used in most economical trapezoidal? It is b plus 2zy by 2 should be equal to y into root of 1 plus z squares. This gives a relation between b and y. So if you substitute z as 1, because it is given as, okay, 45 degrees. If slope is 45 degrees, then z is 1 is to 1. So 1 horizontal to 1 vertical. So substitute, so b plus 2 into 1 into y by 2 is equal to y into root of 1 plus 1 square. So that comes as, so b is equal to 0.828y. So now we get a relation between b and y. Now take in the area formula, that is y into b plus zy. So now keep y same. So what is b here? 0.828y plus z is 1, so 1y. So it becomes 1.828y square. Now since the discharge is given, so q is a into v. So what is v? It is c root rs. So now substitute the value of q as 2.2, area as 1.828y square, and c is 55. R is, you know that for most economical channel section, even for trapezoidal it is y by 2. So I have substituted y by 2 raised to the power of half, and slope is also given, which is 0.00083 raised to the power of half. So solving, only unknown is y, so we get y, which is 1.029 meters. So now take this y and substitute here, and you will get b. So therefore b is 0.852 meters. So that is what asked in this problem. So you have to find the bottom width and the depth if all other quantities are given. So taking the next section here, a trapezoidal channel of side slope 2 horizontal. So therefore z is h by v, so 2 by 1, so z is 2. So it is designed to carry 15 meter cube per second, and the slope is given as 1 is to 5000. So that is 1 divided by 5000 is this. So you have to determine the dimensions of the efficient section, that is b and y has to be determined. Manning's n is given. So now first step is to calculate b plus 2zy by 2 should be equal to y into root of 1 plus z square. You substitute the value of z here, so 2 into 2 into y. Okay, here you substitute 2. So simplify root of 1 plus 2 square. So that finally you will get, take this to this side, deduct here. So you will get b is equal to 0.4721b. So now you will get a relation between b and. So now calculate water area. So water area is y into b plus zy. So you know that b is 0.4721y plus z is 2, so 2y. So you will get 2.472y square. Now you know discharge, which is 15. So therefore area is 2.472y square. So now n is 1 by n 0.014. R is y by 2. Okay, R is y by 2. So this also you have to be very careful. So R is y by 2. Then S we know, so you can substitute here. So in the previous problem I think Chassis equation was used, here it is Manning's equation. So therefore we'll solving this, we'll get y is 2.329 meters, and b is, you know that it is 0.472 y. So substitute in that and get b as 1.1 meters. So we solved two problems of trapezoidal sections, each one taking Chassis equation as well as Manning. Okay, next problem is that a trapezoidal channel has a side slope of 1 horizontal 2. So okay, here z is now h by v, so it is 1 by 2, so therefore z is 0.5, therefore, and the slope of the bed is given 1 is to 1500, which comes to 0.00067. Area of the section is given, so a is given as 40 meters square. So to be careful, find the dimension section, it is most economical. You should also find the discharge for the most economical section if C is 50. Also calculate the area of the lining required. So for first, as usual, as we have the for most economical trapezoidal section, B plus 2zy by 2 should be equal to y into root of 1 plus z square. That is half the top pitch should be equal to length of the sloping side. Now substitute the value of z as 0.5. Substitute the value of z here 0.5 and solve it. So that multiply 2 here and bring this 2 into 0.5 into y this side, so you will get b is equal to 1.236 y. So what is area? It is y into b plus zy, but the area is given here, so the area is 40. So now y here, y into b, instead of b you put 1.236y plus z is 0.5, so 0.5y. So now you will get 1.736y square should be equal to 40. So that will enable us to calculate y, so which is 4.8 meters. So since you know the relation between b and y, you substitute the value of y here and you will get b as 5.93 meters. So this is how you find the dimension sections if it is most economical. So now finding the discharge. So what is discharge is area into velocity. Since chassis constant is given, C root RS. So V is C root RS. So area is 40, C is 50, R is Y by 2. So what is Y? It is 4.8. So it is 4.8 by 2. So to the power of half, and S is also given, so hence discharge can be calculated, which is 80.2 meter cube per second. So only thing is that it is the area of the lining. So where the lining is given, so okay, so if the lining is given generally like this to the sides, beds, and like this. So it is a concrete lining or anything. So it is nothing but the perimeter into length. So length is not given, so you take it as 1 meter. If you are able to find the perimeter for this problem, so you simply multiply by 1, so that will give the area of the, it is not, this is water area, but I want area of the lining. So therefore again wetted perimeter is b plus 2y root of 1 plus z square. So therefore substitute the value of b and y and z, so you will get 16.66 meters. So therefore multiply by 1, so the area of the lining is 16.663 meters square. Now next problem, trapezoid channel, a side slope of 1 horizontal, 1 vertical, so z is 1, is to design to convey 15 meter cube per second. So therefore discharge is given, but a velocity will be given. So it's the same as the previous problem, their area was given. So now we are able to calculate the area. So 15 divided by 1.5 will give the area. So that's the same type of problem. So here, so again take this equation that half top width should be equal to length of the sloping side. So then b will be equal to, so substitute the value of z as 1, z is 1, and solve it. You will get b equals 0.828y. So you know area is y into b plus zy, but b is 0.828y, z is 1, but then the thing is area can be calculated. So area is nothing but, okay, area is here, so which is calculated already, q by v, which is 10 meters square. So you substitute 10 here, and then you can get from this relation, so y. So y is 2.34 meters. So again put it here, so you will get 9.828y, so you will get b as 1.94. So also calculate the area of the lining. You should calculate perimeter. So b plus 2y root of 1 plus z square. Knowing b, knowing y, knowing z, you can calculate the perimeter. So perimeter into 1 will give the area of the lining required. So this is how you solve the problem. So I had given in all the previous problem that it is one horizontal, one vertical. In this case, the angle is given, so that's the difference. Otherwise, the rest all remains the same. So trapezoidal section we have to excavate at least cost, so therefore it becomes most economical channel sections. So given the discharge 14 meter cube per second, bed slope is 1:2500, Manning set is 0.02. So now here it is that tan theta is nothing but 1 in z, so z is 1 by tan theta, which is tan 70, 1 by tan 70, which comes to 0.364. So henceforth take z as 0.364 if any angle is given. So angle is given, then tan theta should be equal to 1 by z, so therefore z has to be 1 by tan theta. So it's the same problem. So b plus 2zy by 2 should be equal to y into root of 1 plus z square. Substitute z as 0.364, substitute z as 0.364 here and solve it. You